I remember there being an argument in the paper I didn't understand, but yeah, it may not be mixing. It probably doesn't matter.
This is the ejector velocity. As I promised it.
Okay.
Yeah.
So this is just some kind of set off. It's just going out and
Yes. So
sweeping a mass. But okay.
Yeah.
I thought that was the original picture.
It's a mass thing, though. I mean, it's you're doing set off. You're doing set off. The standard snowplow phase, right? So once you've swept up the amount of mass that you have, you go to a phase where you're radiated.
That's what Chin did was.
Sorry.
That's what Chin, in their calculations, they assumed that the R process only mixed with as much matter until it
This is just the velocity of the ejector.
Right.
But the
it's not what you want to use to do how far it will extend.
velocity defined by the I calculate the total kinetic energy and the total mass of ejector, and from the E equal to 0.5 times mv square, we calculate the average velocity.
But that's not what you want to do if you want to say the extent.
Oh, I can show you some distribution, but it's now preliminary, so I cannot show you.
In general, I think if this result is robust, that the amount of ejecta can vary by an order of magnitude for a few kilometer change in radius, and we are lucky enough to know what the merger rate is in 10 years or so. It's an interesting game.
No, it is clear that with 10 to the minus 2 you cannot produce enough. There is no chance that the merger rate will go up by a factor of 10. I don't see how it will go up like that. So if it's 10 to the minus 2, it's focused.
But again, this is just a dynamical ejector, and you could get a lot more.
This includes everything. So as I show you the for example, in this DD2 model, the neutron-driven component is also included.
But it doesn't include any accretion disk.
Yes. There's no time scale is about up to 50 milliseconds. So
right.
Yeah.
So now the stuff that's coming out on a second time scale.
Yeah.
Which could be.
Yes.
Could be dominant even.
Mm-hmm.
And you also have equilibrium somewhere.
Yes, but in the case of black hole neutron star merger, my expectation is that I think there's no shock interaction and the temperature is low, so that the situation is much similar to the previous Korobkin result. Universality cannot be.
More massive.
Yes, more massive. But I think simple model contradict with the universality of the process pattern. If the binary black hole neutron merger to be origin of our process, mass is okay, but the universality is not.
Why do you say that?
Simple. We need some other component, but in the case of black hole neutron merger, it is a bit difficult.
Oh, you say you don't have the other component in the neutron star merger, but you could have it elsewhere.
Why the entropy is low in black hole neutron? Because the tidal disruption is the main mechanism for that.
Yeah.
You're saying that the YE is too low
to
produce the lighter R process
Yes.
element.
Yes.
That's an interesting problem. We never had that problem.
So the ejected mass that you are calculating, is it bound or unbound?
This is unbound. Everything is unbound.
Unbound.
Yeah.
And how far do you have to go to be unbound? Like,
How far?
yeah.
In our simulation, because the ejector goes into the homologous expansion phase, so until the flipped matter is comparable of the ejector mass. So I don't know the exact mass, but very far.
You said you don't see the neutrino-driven winds.
In the VHK, yeah.
In the case of a hypermassive neutron star, isn't it surprising that you don't see it?
Sorry.
Even in the case of a hypermassive neutron star, right?
We in the case of hypermassive neutron star, we see.
Oh, okay.
But in the case of black hole forming cases, because the neutron luminosity is low, we don't see.
Masses of the totals in space?
0.1, order 0.1, yeah.
So in the case, okay, that's an interesting question. So if you have stiff equation of state,
Yes.
you form a hypermassive neutron star.
Yes.
You eject small YE material because of the tidal tail.
Mhm.
And then why can't the neutrino-driven will produce the low YE material?
So this
the high
is
YE material.
it's a difficult question because so lifetime of neutron star hypermassive neutron is surely long, but the neutron temperature and the luminosity is lower because
Temperature is
yes,
low?
because less compact nature of the neutron star. More compact star for the same mass, more compact star shrinks much and the temperature becomes higher. And considering the non-linearity of the neutron heating to the neutron temperature.
So it might be that you're not waiting long enough in your simulation.
Right.
I mean, if you go to 1 or 2 seconds, if you look at what the hypermassive neutron star is doing at 1 or 2 seconds,
Yes.
it's probably going to look like, a protoneutron star with 5 MeV neutrino sphere temperatures.
So I think you're just saying that the neutron star has to survive longer
Yes.
to compete with what you're saying is
Yes,
ejected
yes,
dynamically,
yeah,
just
yeah.
because it has a lower neutrino luminosity than
Yeah.
this
yeah.
kind of burst you get
Yes.
at the beginning. So you're just saying that if the hypermassive neutron star lives long enough,
Mhm.
it can produce enough wind that it could explain the first peak. Or you're saying it can't. Is that what you're saying?
I don't know.
So up to what time do you follow your simulations? I mean, when you do the stiff equations of
Okay,
state,
so the exact number is due to Albino, but our result is consistent with their result, and the expected extrapolated number of the ejected mass is about 10 to minus 3. We cannot make 10 to minus 2.
How long do you actually run your simulations for?
15 milliseconds.
15 milliseconds
Yeah,
after the
16
merger.
50 or 16 milliseconds
Yeah,
after
yeah.
the merger. So I think the expected lifetime of the hypermassive neutron star in stiff equation state is 1
Second.
or 2 seconds.
Yeah.
Because of the cooling, neutron cooling. Thermal pressure support the hypermassive neutron star. So.
No, I think most people would say it's rotation that's supporting it.
Primary force is a rotation effect.
Yeah, yeah.
The secondary is a thermal effect. And if you consider
I mean that yeah.
So generally, the neutrino luminosity will be roughly constant for the first cooling time. So
Yes.
if you're finding 10 to the minus 3 solar masses in 15 milliseconds, if it
Mhm.
survived for a
Mhm.
second, you
Yeah,
get 10
yeah,
to the
yeah.
minus 2.
Neutron luminosity almost order of 10 to minus 53 in past 1 second.
Right.
Yeah,
Okay.
yeah,
So I'm
yeah.
just saying, if it survived that long,
Yeah,
you could make
yeah,
enough.
yeah.
But we don't know if it survives that long because it would depend on how fast it would lose its rotation.
But according to, I think that
Yeah.
several times 10 to minus 3 for the
Yeah.
200 milliseconds,
Yeah,
right?
roughly.
Yeah, yeah. So still difficult to make 10 to minus 2.
Right. But there's the viscous driven, there's other things that could contribute. So can I play the devil's advocate here? Sorry.
You may.
Yeah. So there are these simulations of these magnetorotational driven supernova,
Mhm.
which we admit are probably a rare class of supernova.
Mm.
But these simulations by Winteler et al., for instance, they find about, I think, 8 times 10 to the minus 3 solar masses
Mhm.
of low IE material, maybe 10 to the minus 2,
Mhm.
say. So if these magnetorotational supernovae were as common as binary neutron star mergers,
Mhm.
they could, in principle, produce
Yes.
our process in the
Yes.
galaxy. So to put that in perspective, I think that would be approximately the rate of these hypernova that we know of, which are the supernova that have energies that are 10 times higher than those of normal supernova, and Chris and others have argued that they can't be blown up by the standard neutrino mechanism.
Mhm.
Probably magnetic fields are involved in exploding those stars.
Mhm.
So to me, it seems another story you could tell instead of the mergers is that hypernova with magnetic fields.
Yes,
So everyone
yes,
always
yes.
begins these
Yeah,
talks
yeah,
by
yeah.
discounting the magnetorotational supernovas.
So
I don't
this
see-
is exactly the story I'll give you next week. I'd like to compile all these three.
Okay.
Yeah, the three assumptions and three issues, and to explain all of them, the binary merger scenario is one of the.
It's favored.
Yeah, yeah.
Somehow if I add, okay.
Now, how does this magnetorotational supernova, as far as the nucleosynthesis goes, how would that differ from magnetorotational jet in one of these events with a hypermassive neutron star?
I don't think it would. So if you had, I mean, right? I mean, I think if the neutron star you're forming in these systems had very strong magnetic fields, you probably would predict much higher
And
ejected masses.
yes,
Why?
and my concern about the magnetorotational scenario is that on the one hand we need some strong magnetic field.
Yes, you probably do to make.
Yes,
GRBs.
but on the other hand we need rapid rotation. Rapidly rotating strong magnetic field star is somewhat contradictory.
That is true theoretically, but we also
Yeah.
see hypernova, and you know,
Yes,
there
yeah,
definitely
yeah,
is something
yeah.
that is doing this.
But I'm not sure that the hypernova is due to magnetic rotation.
Can you get it through neutrino mechanism?
Yes, because the neutron luminosity is
Even
completely
Chris should
different.
argue.
Yeah.
You think that you could get to 10 to the 52 or
The
supernova?
fact that you cannot get something from one phenomenon is not a proof for another phenomenon. This is a common mistake in this field.
Okay.
Yes. So we take three. Two.
No,
One
I'm saying
assumption
that the fact
for
that
the
you
one.
cannot produce hypernova, let's say that you prove that you cannot
I
produce
know.
hypernova by this, it is not a proof.
Okay.
It's
No, it's not a proof. I'm playing. I said I'm playing the devil's. I prefer them to be mergers. I like that idea, but
But we have a large number of sort of GRBs, and not one, but the several is highly correlated. So if you want to answer all these issues, one scenario is binary merger scenario.
thank you.
We can take a short break and people can go up for discussion if they want to.
Okay, thank you.
Let's thank you, Chair.